Hello everyone, my name is Shashank and I'm a PhD candidate in Reza Moini's lab at Princeton University. Firstly, I would like to thank Rilem and Rilem Youth Council to provide me an opportunity to present my work here. Today in this webinar, I will be talking on tough cortical bone inspired tubular architected cement-based material. Let's start with a bit of a background. Ordinary concrete has limited ways to dissipate energy in the process of fracture. This is due to limited toughening mechanisms such as crack shielding, due to micro cracks, crack deflection, crack aggregate bridging, crack closure induced by surface roughness. And these limited toughening mechanisms leads to relatively small length of fracture process zone. Therefore, not to our surprise, concrete material are either brittle or quasi-brittle under tension. Now, the question I would like to ask whether we can develop tough concrete without changing composition as a new way to enhance the inherent resistance of cement-based material to fracture. In other words, can we engineer cementitious material to have fracture resistance? Um, what can help us to develop these material is the flexibility provided by the fabrication processes and the opportunities provided by the design of the material structure. Now, the material structure can be either microstructure or mesoarchitecture. The design of material architecture be, can be used to tune the fundamental properties of the material to obtain the desirable performance, in contrast to the monolithic uh, brittle solid. This further helps us to overcome the mutual exclusivity between strength, toughness, and stiffness. Today, I will be only focusing on the strength and the toughness aspect of the material. When it comes to design, can we learn from nature? Let's look at the microstructure of the bone. So the human femur bone is composed of outer tough cortical bone and the inner porous spongy bone. The cortical bone has two-order higher fracture toughness than its constituent material, hydroxyapatite crystal and collagen. This increase in fracture toughness can be attributed to the presence of tube-like osteons embedded in the cortical bone. These osteons are weakly bonded to the organic matrix uh, through these cement line. The cement line has nothing to do with the cement, just to avoid any confusion. The cement lines are 10 times weaker than the osteons. So when the crack start to propagate in the cortical bone, these weaker cement lines provide microstructurally preferred path for crack to propagate, hence triggering toughening mechanisms like crack deflection through cement line interaction in cortical bone. Taking the inspiration from the cortical bone, we want to engineer these toughening mechanism in the brittle cementitious material using tubular architecture. Furthermore, by tubular architecture, we mean the tubeless cement line around the osteon, not osteons themselves. So let's see how do we fabricate them. Firstly, you can directly 3D print them. To do so, we have developed parametric contours like graded sinusoidal and elliptical to print tubular architected material by defining the input geometrical parameters. These contours can then be converted to G code. In order to execute the whole process, we have developed in-house algorithms in Grasshopper and Rhino. Furthermore, there are several approaches to contour the toolpath. However, I won't get into the details for the sake of time. Another method that we can use is a hybrid process in which we 3D print a PVA mold, then cast urethane rubber into it and demold the PVA to make this urethane rubber mold. Then we use this urethane rubber mold to cast the cement paste. This method enables direct formation of tubular system in cementitious material. And this is also the approach that we have used for what I will be presenting today. Um, Let me expand a bit on design parameters. So we have fabricated tubular architected material with porosity varying from 20 to 50% and aspect ratio varying from 1 to 3, where 1 denotes the case of circle and the any other value denotes the case of elliptical design. These parameters corroborate well with the volume percentage and the aspect ratio of the osteons in the cortical bone. Furthermore, I will be only highlighting the case of circular design with 40% porosity and the elliptical design with 40% porosity and aspect ratio today in this presentation for the sake of the brevity. The mechanical response was characterized by modulus of rupture and fracture toughness. The modulus of rupture was characterized using the ASTM C78, and for fracture response, ASTM E1820 was used. In fracture, the compliance method has been used for crack extension, and combined J elastic and J plastic terms have been used to calculate the fracture toughness as the crack propagate. We have also plotted R curve to show the resistance to crack growth in terms of the fracture toughness. So what did we find? Let me show the highlights of some of the results for some of these designs. So the load displacement response of notch specimen demonstrate that the architected tubular material that is being represented by blue color and the red color shows a unique non-brittle fracture behavior compared to the brittle solid counterpart showed by the gray line. The architected tubular design demonstrate multiple hardening and softening behavior, which is evident from the multiple crack initiations. The R curve shows that the toughness of the tubular architected material increased with the extension of the crack in a stepwise manner. This increase is directly correlated with the load displacement plot, where the softening corresponds to the crack extension and the hardening corresponds to the steep increase in the R curve. We hypothesize that the stepwise cracking through the tubes is the toughening mechanism which lead to an increase in toughness. To better understand the crack propagation in the tubular architected material, we carried out digital image correlation on the fracture rest. You can see that following the crack initiation from the notch, the softening correspond to the crack extension in the both circular and elliptical design was observed. On the other hand, each hardening corresponded to the initiation of the crack from the tube. These experimental findings from DIC validates the hypothesis of the stepwise cracking. More importantly, when we look at the specific crack initiation and crack propagation fracture toughness, the specific crack initiation fracture toughness remains unchanged, which is a good news because that means we can increase the porosity in the material while maintaining toughness. When we look at crack propagation fracture toughness, an increase of 3 to 5.6 times from solid material to tubular architected material was observed. And all this happened while the specific strength remained constant, which is again good news. For a better understanding of the toughening mechanism, we looked into the theoretical analysis of stress and density factor and stresses at failure of crack in the tubular architected material. A stress intensity factor is used to predict the stress state near the tip of the crack or notch caused by the far field stresses, that is sigma x infinity. The stress intensity factor in the presence of a tube can be defined in terms of the stresses on the crack in the uncracked body due to tubular elliptical void, as shown by this blue sigma x. Now, the sigma x can be obtained using the Mushkel's-Rayleigh equation. We are also defining the stress intensity factor ratio, which is simply the ratio of the stress intensity factor of material in the presence of tube over that of a solid. The SIF ratio, um, defined as F, will aid to easily look at the effect of the presence of tube relative to its absence. That is the case of the solid material. Now here I'm showing the plot of stress intensity factor and far field stress in the solid and the presence of and in the presence of the tubular void of circular 40% and elliptical 40% with the aspect ratio of 2.5. So in a brittle material such as cement base, crack initiate when the stress intensity factor becomes equal to critical stress intensity factor, according to the Griffiths energy balance approach. Consequently, the intersection of stress intensity factor and far field stress plot with the critical stress intensity factor yields the far field stress at which the crack initiation takes place, as shown by sigma x infinity solid. We can see that the stress at failure in the tubular architected materials is smaller than the stress at failure of the solid. Given the previously presented definition of stress intensity factor ratio, we can define the stress at failure in tubular system as the stress at failure of the solid counterpart over the SIF ratio. In the same way, the load at failure in the tubular system can be also defined in terms of the SIF ratio. Using this SIF ratio, we can also look at the effect of the tube size and shape. Based on our discussion the last slides, we have calculated the stress intensity factor ratio for different porosity and aspect ratio of tubes. For solid system, in the absence of the tube, the SIF ratio is 1. That makes sense. We can say that this presence of the tube position in front of the crack increases the stress intensity factor at the tip of the crack. The SIF ratio increases with the increases in porosity, and it decreases with the increase in aspect ratio, which is an interesting finding. Using the relationship between the SIF ratio and the load at failure, we have also plotted the theoretical load at failure for different porosity and aspect ratio. We can see that the theoretical load at failure decreases with an increase in porosity and increases with an increasing aspect ratio. The theoretical trends for the single tube also match the experimental trends of the load at failure for a fully tubular system. The results regarding the load at failure indicate that the tubular system with higher porosity and lower aspect ratio exhibit a lower load at failure, which negatively affects the fracture toughness of the cement-based material. However, the same characteristic of higher porosity and lower aspect ratio in the tubular architected material facilitate the stepwise cracking, which in turn increases the material's fracture toughness. Hence, we can say that load at failure and stepwise cracking have competing effects on the failure toughness. If you look at the broader range of the tube size and shape, the competing effect of load at failure and the stepwise cracking give rise to optimal fracture toughness in certain cases. For instance, among the circular cases, the porosity of 40% exhibits the best fracture toughness as shown by the blue dotted circle. On the other hand, among the elliptical cases, the porosity of 40% and aspect ratio of 2.5 exhibits the highest fracture toughness as indicated by this red dotted circle. The theoretical analysis that I showed before for the stress intensity factor was conducted for a single tube. The superposition of multiple tubes and the positive and negative effects of their location on a stress intensity factor can be considered to better capture the experimental analysis. It is also interesting to note that the SIF ratio of the crack tip increases or decreases depending on the position of the tube um, from the crack tip. The theoretical determination of the stress intensity factor can be extended for better comparison of experiments and analytical model, considering both the superposition of the effects of multiple tubes at various locations ahead of the crack tip, as well as the bending stress state. To put it all together, let's see where does all the sample lands on the Ashby plot. So all the tubular architecture material exhibited higher specific fracture toughness than the reference cement base. Tubular architecture material shows fracture toughness in the range of mortar to the upper boundary of the granite. Zooming into the plot, we can see that circular 40% shows specific fracture toughness close to the upper boundary of the fiber reinforced cement base, whereas elliptical 40% with the aspect ratio of 2.5 showed the highest specific fracture toughness among the tubular architected material, and it is even higher than the fiber reinforced cement base. In conclusion, we showed that hybrid or additive manufacturing can be used in a variety of ways to architect material. However, further work on scaling up is necessary. We also learned that toughening mechanism inspired from bone can enhance the fracture toughness of brittle cementitious material up to 5.6 times. The stepwise toughening mechanism can be further engineered by the competition between the tube size and shape on the failure stress intensity factor and load at failure. And finally, considering our first question, can we make a brittle material tough and non-brittle without changing composition? Yes. By engineering the architecture, we can achieve toughness strand trade-off without changing the composition. Digital workflow for additive fabrication can help make realization of these materials more viable and accessible. Moving ahead, I would like to thank my advisor and director of the AM2 lab, Professor Reza Moini, for his support over the last few years. I'm also grateful to fellow graduate students, postdocs, and undergrad in our team for their innovative contribution through several discussions. I'm also grateful to NSF Career and NSF ECI for the partial funding of this project. Thank you for your attention. I'll be happy to take any questions now. Please also feel free to contact me if you have any more questions or suggestions through the email. Thank you.